Hello YouTube viewers, welcome to my show Science Thursday. In today's episode we're going to talk about 110 volt system, why America still uses it. America, Canada and Japan still uses this. So first you have to take a closer look at the physics aspect of it. Don't worry, there is not too much math about it, but all you have to understand is that at the end of the day, what matters. Basically, what is the real power? You're not gonna go to somewhere and be like, okay, I want this voltage or that amperage. No, that's not your job. What you're gonna say, hey, I want basically a motor that is like, let's say 2 kilowatt. I want basically water pump that is 5 kilowatt. You only deal in watt. Basically, that's the end of the it. Now, watt is not something like a physical quantity. It's not like 1 liter of milk that they're gonna, hey, here's your 10 watt, here's your 20 watt. So what we do is basically we give you voltage. So this is the job of basically your electrical provider. They're gonna like, okay, we're gonna give you this much voltage. This is fixed. It's not gonna change. Now, what you're gonna do is basically apply load to it, aka ampere to it. Basically, if you read closely any electrical label on any electrical appliance, it will say 5 ampere, 2 ampere, 10 ampere. These sort of things simply translates to take that ampere, multiply by that voltage. Basically, in American case, 110 volt. That will give you basically if there is 110 volt and some appliances says I'm gonna use 1 ampere. That means you have 100 watt plus load. Basically, your actual electricity bill will charge you 100 watts. Now that's the watt aspect of it. Now that means you have to worry about voltage and amperage. Now voltage and amperage, they do not interact with each other without any consequence. There is a consequence to that. Consequence is known as ohms. I hope I don't get flagged for this image, but basically this ohms is what we call resistance. This resistance is present in every cable unless you have superconductors. Now barring that you don't have superconductor, you have to deal with the fact how you're going to handle it. So we sometimes use ohms to our advantage. Basically every fuse you have, old fashioned, basically something that used to melt, is basically relying on the fact that if the current flow in your equipment or something like that goes too much, basically let's say the appliance was built for 5 ampere and you sent 10 ampere to it, the fuse gonna blow up because it's gonna melt because of the heat. Now that's awesome and everything is great about that for fuse appliances, but you have to understand we don't make everything out of fuse. We need something to carry electricity, and the something that we need to carry electricity must be reliable enough that minor fluctuation does not end up melting it. To make sure that we do that, we simply have two choices. Choice number one, make the cable thicker, because thicker cable has less resistance. Now this may sound inverse, but just go with it. Basically, the thicker the cable, lower the resistance. Or let's say there is a limit to it. Basically, you can't just keep making cable thicker and thicker. You can't have a cable that is size of an arm. So to manage that, basically, so your cable does not become like ludicrously thick, 1 meter thick or 10 meter thick, we increase the voltage. This is why you have high voltage transmission line, for this simple reason, basically to reduce the ampere, because we can handle ohms to a certain extent. You can have a basically let's say 10 ohm cable, basically a cable that can handle 10 ampere, a cable that can handle 20 ampere, but you cannot have a cable that can handle 12,000 ampere. So to make sure that if we have to transfer 12,000 ampere, basically that much watt, what we do is basically bump the voltage, because ampere and voltage are proportional to each other. So if you still have to send only 10 ampere, you increase the voltage. So ohms, we keep fighting with it, and we always try to strike a balance. We want to make cable as thick as possible, as long as we can afford it, and make the voltage as high as possible, as long as we can safely handle it. Because if you want to like have two conductors next to each other and you're not touching it, basically you have one neutral, one grounding wire and one main live cable. If you have these two, you have to understand, if the voltage goes too up, it will directly jump. Why? Because there is air, because earth has atmosphere. That air starts to get ionizing. So we cannot have a scenario where you have two conductors next to each other and as much voltage as you want. It's going to become plasma in between of them. To make sure that that does not happen, our high voltage line, if you pay attention to them, you will always notice A, the conductor is naked, B, the conductor is very far apart from nearest metal. So at every scenario, every case is thoroughly understood. Basically, if you just look at, I would urge you to just look at a high voltage transmission line, you will notice that conductor never comes close to the metal structure itself. They always try to make sure that it's minimum of few feet apart, minimum of that. Higher the voltage, the bigger the gap they have to give. So that is how we handle it. That's why we don't have 10,000 volt coming to your home. And it also mentioned, it is very dangerous. Now be mindful, as long as you are below 70 volt, you are safe. You can touch it, you won't get electricity flowing through you. The moment it crosses 70 volt, you're gonna die. So 110 volt is gonna kill you, same as 220 volt. Don't worry too much about it. Basically 70 below, awesome. 70 above, you dead. So that's the physics aspect of it. Then the question becomes, why the hell we have three-phase power? Okay, you have to understand it this way, like in terms of DC electricity, if I have to simplify it, think of it as a band saw, basically a saw that goes from point A to point B, basically completely circular. This is what your battery does. So that's why you have positive conductor and negative conductor. Awesome, everything works, but that's not efficient. So what we do is we created AC system. AC only relies on basically one conductor. Benefit of that, it's like a saw, normal saw that you are doing back and forth, back and forth, back and forth. This back and forth is happening with electrons. You don't physically push electron. Okay, electron go from point A to point B, point to C to point D, then come back to the negative terminal. You simply have electron, a positive force, negative force, positive force, negative force. But you can see, even though you are not physically moving away or backwards, you're still getting work done. This is the majesty of AC current. And the neutral, then you'll be like, okay, if one cable can do that, why the heck we need neutral? The reason for that is, if you don't do that, the thing that is getting that electricity will become energized. Basically what we saw, it will reach the same potential as the cable, so it will not do the work. You need to provide what we call zero ground, basically ground reference, zero voltage, because if you don't, it will hold the charge. It's like, okay, I am now charged, I won't work anymore. So neutral is just for grounding and to provide that zero reference. So if you directly try to hang a bulb and directly let the neutral wire go, it won't work, because of course it will work for that microsecond when the electricity started to flow, but once the flow happened, the electrons are like, yeah, I'm here, I'm not going anywhere, because even though you are still doing this, you need something to do it against. That against is that 0 point or neutral or grounding. So somebody came up with the idea, what if we have to transfer 3 times the power? Let's say instead of 100 watt we want to transfer 300 watt. So instead of using 6 cable, why not use 3 cable? Now why 3? One simple reason. If you have basically motor, you have to understand it. Motor is the backbone of humanity. If motor goes, we go. Like motors are important. Motors run your refrigerator, motor runs your air conditioner, motor runs your water pump, motor runs your grain crushers. Basically, if motor is there, awesome. Motor dies, you die. So when we have simple single phase motor, it works, everything is nice and dandy, but you have to understand, because the voltage goes to 0 and then negative, during that time when your voltage is 0, either your motor is not going to do anything, or during that 0 voltage your motor is torqueless, because voltage is what's applying torque to your motor. So it's the turning power is not there. Now that creates a paradox. How the heck you're going to keep running motor if every few seconds the voltage goes to 0? We use capacitor to give that initial jolt, and then inertia takes care of us. Because if you start spinning something, let's say a top, and you are keep blowing on it or rotating it some other way, it will keep spinning. So that's fine and dandy for small loads. This is crucial part. This is more than enough for small loads. But when you have something big, let's say you have big water pump, a pump that is so big that is pumping 10,000 liters of water per minute, in those sort of scenario, the feedback, basically the load that is on your motor, that can reverse track it. To make sure that that never happens, we apply 2-phase. Now here's the problem with 2-phase, it's not enough. No matter how you lay down 2 sine wave frequency on top of each other, you can never get a scenario where there is no 0 point. So if you have 180-degree offset, basically you shift it, you're like, okay, I'm gonna shift it, yeah, you get 2 peaks, but you still have a scenario where the voltage goes to 0. That's why we have 3-phase. You can overlap in such a way that no matter what happens, the voltage never goes to 0. So if you have high torque demand, basically big lift elevator motors, no matter what happens, no matter what kind of torque or load is on them, it will never backflash, because the voltage never goes to 0. And this also has the extra advantage that you don't need capacitor to start it, and plus if you want to change the rotation, you just change the 2-phase. So that's awesome. That's why we use this system. And why do we have phase offset? Why do we have 120-degree offset? First, for that overlapping. Second, because of how maths works out, and you have 3-phase add basically 120 to each other, you get 0-degree benefit. That means if you have these 3 wires connecting to a single point, at some point in time that point, basically that quote-unquote neutral, becomes 0. That is why you can have 3-phase motor that only needs 3 cable without needing that neutral reference point, because you don't need the voltage going down. Because if voltage 1, let's say phase 1 is going to 100 volts, phase 2 is going at the lower voltage, phase 3 is at very low voltage phase. So for this reason, it itself creates its neutral. So that is why we use 3-phase. Now then the question becomes, why the heck European, Indian, China or Russia, almost majority of the planet Earth, why the heck they are using 220 volts? You have to understand, it reduces the ampere. I told you, either you use thicker cable or you increase the voltage. So we simply thought of increasing the voltage. Then a single connection, basically let's say I have a simple plug, aka basically earthing, live and neutral. You have a simple plug, we can draw upwards of 3 kilowatt Now, if you are familiar with your electrical appliances, you must have noticed every single appliance that is made for single phase is limited to 1500 watts. In case of India, or basically most of the world that does not run on 110 volt, it's not the case. We can go upwards of 3 kilowatt safely. Basically every single circuit breaker that we have in our system is rated for 15 ampere, same as USA. But because the voltage is so high, we can draw upwards of twice the power basically. And when we do 3 phase, that translates to 440 volt. Now remember, like, why does not it go to 600? Because the phase offset. So at any point, the maximum you can get is like one phase would be at peak, another phase would be at the bottom. So peak is plus 200, minus is minus 240. So at that way you get the potential difference. That is why voltage is always referenced as potential difference. It's not about like minus or positive, it's about difference. So basically that difference is of 440 volts. No matter what you do, you cannot get the potential difference of 600. So that benefits us in terms of motor construction. Our motor becomes cheaper. So if you have a 3-phase motor that is running on 440 volt, is cheaper compared to a 220 volts. That's why our motors are also cheaper. On top of that, insulation. Now you must be familiar aspect of the fact that every cable has to have insulation, especially if it's for consumer use. Basically, if you and I am going to use it, it must be safe. You have children in home, you have doggies at home, you have pets at home, and you don't want your home to catch fire. You don't want to go into shower and get electrocuted. So we must rely on insulation. Now here's the aspect of voltage. That voltage does start to get very emotional at higher voltage, but does not go directly. So it's not like this. It's not a linear curve. It's a what we call exponential curve. So at 300 volt, it's not making that much of a difference. Electrons are still calm and steady. But once you start to reach 500 or 600, it becomes emotional. It starts to jump. Basically, you have to make sure bare minimum, make sure you have gap of 1 inch of air to make sure the electricity never jumps. Now, of course, that is worst case scenario. That worst case scenario is built in such a way that what if you have flooding? What if you have rain? What if you have two conductors exposed somewhere and something goes in between? You don't want like electricity using that to cause a short circuit. So that is why we limited it to 200 volts, because all research suggested that we can push it a little bit further, but you don't want to take risk to that extent. 100 volt is too less, so 200 is what we satisfied on. Now conductor, this is the reason why European Union jumped on it, and not European Union, everything jumped on it, even India, because you have to understand, India has a ludicrously huge population. Now to give you a context of it, if you remove 1 billion people from India, the remainder will make America. So understand that, and America is the 3rd or 4th largest country in terms of population. So we have ludicrously large amount of people, so we can't provide enough copper to everyone to have basically enough electrical needs. So the fact that it requires less conductor, aka copper or aluminum, it actually helps us. Basically, it allows your economy to grow. So if let's say America has 100 tons of copper versus India has 100 tons of copper, India can supply electricity to larger group of people using that 220 volt. And this was necessary after World War II. Once World War II happened and everybody who was in 110 volt, they had to switch to 200 because they simply did not have enough material. So this is the reason why entire world is running on 220 volt. Now, if you're like 220 volt is so awesome, then why the heck America is still at 110 volt, or Canada for that, or Japan for that? First, you have to understand, before AC became a thing, there was DC, or that DC had a problem. Basically, DC was you cannot up the voltage or downgrade the voltage, but somebody figured out how to make a generator that directly created 110 volt. That 110 volt was directly delivered to your home using super thick cable, and I'm talking cable that are bigger than my arm, basically thick, very thick cables. Now that created the first electrification in America. Basically, you first time in entirety of America, you have electricity. Electricity is reaching your home using 110 volt of potential difference using DC. Now every appliance at that time, aka arc lamps at that time, that was running on 110 volt. Now once Nikola Tesla comes along, it's like, bro, let's go to 200 because like entire of the planet is using it, you should use it too. They're like, no, we have to change our basically infrastructure. That's why they are stuck with basically DC power. Basically they're still stuck with 110 volt because the foundation of America's electrical grid, which was DC by the way, was made on 110 volt. They did not want to change the appliance. They are like, okay, use 110 volt. Now with AC, even though your let's say generator can be making any random watt, let's say it can be making 5000 volt, you can easily step it down to whatever you need. That was the good part. So they like Nikola Tesla is like, okay, you want to use 110 volt, here's your 110 volt. Now it created a problem that one plug, no matter what you do, cannot provide more than basically 1500 watts of power. Now it's not that it cannot physically provide it, it's just for safety reason. So that means in a 15 ampere circuit breaker in India can provide 3 kilowatt. A 15 ampere circuit breaker can provide only 1500 watts in America. Now that created a problem because they thought of using 110 volt because electricity was beginning to take hold, beginning to catch up, but nobody was using it other than for lighting. Now once motors came along, now once you have dishwasher, once you have washing machine, then it's like, okay, this simply won't work on 110 volt. So that reason they had to create basically either 3-phase, which they have 3-phase for industry, but for home that created a paradox. Basically 15 kilowatt at the early days was not enough. Basically early washing machines and dishwashers, they were very, very power hungry, and not to mention your water heater was also very energy intensive. To how do we make sure that those appliances can be powered? Somebody came up with the idea, why not give 2-phase? So in India or in most of the world, you have 1-phase for small load, 3-phase for industrial load. That's it. In America, you have 2-phase and 3-phase. There is no 1-phase because 1-phase is just not enough for normal household. That is why your washer will have fancy plug and your dishwasher will have fancy plugs. And because America was struggling to preserve that minor investment they had, they got stuck with this. Now you might say, okay, that does not make too much of a difference. Yes, it does. This is a tragedy for you guys. Basically, single phase becomes useless in your country. Basically, flat out, even if you want to build a home and you're like, hey, I only want a single phase, at least to your circuit breaker, they will send you to 2-phase. They have to. It's required by the law. And then how the heck they're gonna give 2-phase? Now there are two simple ways. In Canada, basically, if you watch Electro Boom's video, you will notice his phase. If once he collects that 220 volt system, he gets phase offset that is of 120 degrees. So that way, that simply means they're taking basically 2-phase wire and they're giving him. Now that's awesome and all, but it creates a paradox. If you are, let's say, in a rural area and you have only one cable going to, basically one high voltage cable like this, one high voltage cable, how the heck you're gonna give 2-phase? Because it has only one phase. So somebody came along with the idea of creating what we call center tap. So basically you have one transformer here, one step down transformer, and it has center tap. Basically the coil is built in such a way that from point A to point B, the voltage tap would be around 240 volt, but you're going to take a center tap out of it. So that's why you have one input and 3 output. So center output is basically 0 volt, left side is 220 volts, other side is 200 volts. So basically this is how you run your most system, and that is why if in American system you have 180 degree phase offset, in Canadian system you have 120 degree offset. Side effect, these two are still not enough, because you can notice it. Basically, no matter what you do, I already specified, no matter what you do, you cannot have a scenario where you have 2-phase offset from each other and with 0 voltage. As you can see, 0 voltage, 0 voltage, 0 voltage. This whole section is 0 voltage. So they still need 3-phase, they still need 2-phase, they still need 1-phase. So that created a paradox for them. Basically, American electrical system is simply not efficient enough. A, you are using way too much conductor. B, you have to use fancier transformer. C, your 2-phase systems are not efficient enough, basically because the voltage is going to 0. So it's not like if you are running a very big, let's say, wood saw or things of that nature, you still need 3-phase motor. So that created a paradox. Basically, single phase become useless in America. That is why it's a tragedy. It's not like, oh, it's like American way. No, it's wasteful. Not only in terms of conductor, not only in terms of electrical cost, because every electrician now has to know how to deal with 2-phase, which is very complicated. Every electrical manufacturer has to deal with the fact that the prongs, basically the connector itself has to be designed differently, so you cannot accidentally plug a 220 volt system into 110 volt. And again, industry still needs to have 3-phase. So what was the point? So this is the tragedy of clinging to your past. Basically, this is some American basically politicians like, yeah, we don't want to change, our arc lamps, ancient arc lamps. Yeah, now every American is paying for it. That's why you have to have fancy transformer. That's why your electricity grid is so messy. That's why even a normal home, and this also comes as a side effect that you can't normal home, even though they have more than enough wiring for 3-phase, they don't have 3-phase because 1-phase is extra wasted for that center tap. So in India, you have simply 4 cable coming to you and you get basically 3-phase power. In USA, you have 3 cable coming to you and you don't get 3-phase power. So this is a very weird way to, basically 2-phase, it does work. Like it was a basically what you call stopgap measure, but it does come with a consequence. You have to have fancy transformers. So it's a tragedy. It's not something like, oh wow, like they figured out how to do something. No, you wasted a lot of energy, money, everything. You just wasteful. This is one of those times where it's like, America, you really need to learn. Now, of course, this is the first video. I'm going to make a second video about imperial system, so that will be interesting. So this was my presentation on why America still uses 110 volt. I hope you liked it, learn from it. In that case, please leave a like. If you did, and also click the ad that are shown in this video, that will directly help me. And if you didn't like it, don't worry, you can press dislike. I would urge you to press it twice to show me your extra disappointment. And please leave a comment because I reply to all of them. And subscribe, press the bell icon if you're free. And as always, thanks for watching.